Welcome everyone. In this presentation, we will explore the concept of combinational logic circuits. These are fundamental digital circuits where the output depend only on the present inputs. They are the backbone of all modern digital electronics like CPU, calculators, and communication devices. Introduction. Combinational logic circuits are digital circuits. Output depends only on current inputs. No memory elements. Fundamentals in fundamental in digital systems. So combinational logic circuits are digital circuits where the outputs are determined only by the inputs that are currently applied. This means there is no memory or history involved. For example, if you give a certain input combination, you will always get the same output. They are cor- they are completely predictable and deterministic. These circuits are widely used in devices such as adders, multiplexers, and decoders. Characteristics. So combinational logic circuit doesn't require any feedback or memory. These are time independent. As it has deterministic outputs and faster than the sequential circuits. So combinational circuits have some key characteristics. First, they have no memory, so the output only depends on present inputs. Second, they're time independent, meaning the moment the inputs change, the changes instantly. Third, they are deterministic, so same output combination always produces the same output, unlike sequential circuits, which output depends on the previous output. Basic logic gates: AND gate, OR gate, and NOT gate. The foundation of all combinational circuits lies in these three basic logic gates: AND, OR, and NOT. The AND gate provides a high output when all inputs are high. The OR gate produces a high output when at least one input is high. The NOT gate, also called as an inverter, flips the input if input is 1, output is 0, and vice versa. Every other complex digital circuit can be built using these three gates. So we can see the truth tables of these gates in the slides. Universal gates: NAND gate, NOR gate. NAND and NOR gates are called universal gates because any logic circuit can be implemented using only NAND gates or only NOR gates. This means that even if you didn't have AND or NOR gates, you could still design any circuit using NANDs and NORs. For example, NAND gates are heavily used in digital IC design because they're cheaper and easier to fabricate. So we can see the truth table of the NAND gate below and the NOR gate also. These are called universal gates since we can implement any Boolean function with these two gates. Exclusive gates. One is XOR gate and another one is XNOR gate. Exclusive OR and exclusive NOR gates are special because of their unique properties. An XOR gate outputs 1 when the inputs are different and 0 when the inputs are same. It is very useful in arithmetic circuits like adders as well as in error detection. So on the other hand, an XNOR gate produces 1 when both inputs are the same and 0 when both inputs are different. It is widely used for equality checking, for example, a digital password. Half adder. Uh, The half adder adds two single bit binary numbers and it produces outputs as sum and carry. This is the circuit of an half adder. So it takes two single bit inputs and produces two outputs. One is sum and the other one is carry. The sum is generated using XOR logic while the carry is generated using AND logic. So the next one is full adder. It adds three inputs, and full adder also produces sum and carry. And we can also build full adder using two half adders. And this is the circuit of the full adder. So it takes three inputs A, B, and a carry input, and it produces a sum and carry out. This makes it possible and add binary numbers that are more than one bit long by connecting multiple full adders in a chain. For example, a full adder is built by cascading four full adders. A 4-bit adder is built by cascading four full adders. This circuit is heart of arithmetic logic units in processors, making it one of the most important combination circuits. Half subtractor. We have seen half adder. Now this is half subtractor. Subtractor subtracts two single-bit binary numbers, and it is produces difference and borrow. And this is the circuit of the half subtractor. The half subtractor is used to subtract one single bit binary number from another. It has two inputs, A and B, and produces two outputs, difference and borrow. The difference is generated using XOR logic, and the borrow is generated using NOT and AND logic. Like the half adder, it is a simple circuit but cannot handle borrow from a previous gate. And the circuit is also same like half adder, but there is just a NOT gate. Full subtractor. Full subtractor subtracts three inputs, and it is also produces output, difference and borrow. And we can build the full subtractor using two half subtractors. And this is the circuit of full subtractor. So it has three inputs, A, B, and B in. So this is like carry, and two outputs, difference and borrow out. So this allows us to this allows multi-bit subtraction when multiple full subtractors are connected in series. For example, subtracting large binary number requires chaining full subtractors together. Encoders. Encoders can convert 2 power n inputs into n input and outputs. For example, decimal to binary encoder. This is the block diagram of an encoder. So encoders are circuits that take many inputs and generate a smaller number of outputs, usually in binary form. For example, a decimal to binary encoder converts decimal digits into binary numbers. Encoders reduce the number of data lines and simplify the circuit design. They are widely used in digital systems such as keyboards, where each key press is encoded into a binary code for processing. Decoders. Decoders converts an input into 2 power n outputs. So for example, binary to decimal. This is reverse operation to the encoder. So this is the block diagram of the decoder. So these perform the opposite operation of encoders. They take a small number of inputs and produce a large number of outputs. For example, 3 to 8 decoder takes three binary inputs and activates one of 8 outputs. Then use it in memory addressing where the input address selects which memory cell to access. Without decoders, it would be difficult to implement large-scale memory systems. Multiplexer. So multiplexer selects one input from many inputs. We also call multiplexer as many to one, since it selects one input from many inputs, and the the input which is selected by the selection lines. And this is the block diagram of the multiplex. Multiplexer or mux selects one input from many and forwards it to the output. It uses selection lines to decide which input to choose. Think of it like a railway junction where signals decide which track the train will take. Demultiplexer. So demultiplexer is opposite to multiplexer, and it routes one input to multiple outputs. and takes a single input and routes it to one of many outputs based on selected lines. For example, in communication system, a debug can distribute a data signal into multiple receivers. Together, multiplexer and demultiplexer circuits form a basis of many data transfer. Comparators. Comparators are that compare binary numbers and output where one is equal to greater than or smaller than other. So like a comparator compares two binary numbers. The output is either equal, greater, or smaller. And this is the block diagram of a comparator. So this is the 4-bit number of A and this is 4-bit number of B. These both will get compared. So the result will be equal, greater, or smaller. For example, 4-bit comparator can compare 4-bit numbers and give the result. Comparators are used in decision-making circuits, sorting operations, and digital systems that require logical comparisons like CPUs. Code converters. Code converters change one form of data representation into another. For example, a binary to gray code converter changes binary numbers into gray code, which reduces the errors in digital systems. Another common example is gray code to binary conversion. These circuits are used in digital communication, error correction, and systems where different codes need to be understood by different devices. Another combinational circuit is parity generators and checkers. Generators and checkers are important for error detection in communication systems. A parity generator adds an extra bit called a parity bit to data before transmission. A parity checker checks the parity at the receiving end to detect errors. For example, in even parity, the number of ones in the data plus the parity bit must be even. Applications of combinational logic circuits. Combinational logic circuits have countless applications. They are used in CPUs and ALUs for arithmetic and logical operations. They are essential in calculators for addition, subtraction, and other arithmetic operations by do. They are used in memory addressing, communication systems, control systems, and even small devices like washing machines and remote controls. Advantages and limitations of combinational logic circuits. So the advantages of combinational circuits include their speed, simplicity, and reliability. So there is no need of memory like sequential logic circuits and combinational circuits. Since they're because due to that reason, combinational logic circuits are fast, simple, and reliable. But the limitations are it doesn't have any memory and not suitable for sequential tasks. So they are fast because they don't depend on clocks like sequential circuits. However, they also have limitations. They cannot store data or perform sequential tasks, which means they cannot handle history or state. So to conclude, combinational logic circuits are backbone of digital electronics. They form the basis of arithmetic operations, data transfer, and decision-making logic. From simple calculators to advanced microprocessors, the circuits are everywhere. By understanding them, you gain insight into how digital electronic systems work at the most fundamental level.